shift. And in fact, the next two talks will talk about an even more intimate kind of connection. So a lot of the post-training phases, language models for alignment use things like RLHF. And so we're very happy to have first Wei Xiong from UIUC, and who is a PhD student of Tongjiang and Nan. And he also works, I think, 20% at Google DeepMind, and has thought a lot about kind of various parts of the RLHF pipeline. And so he's gonna explain to us how all of this works. And Wei, please take it away.
Okay. Is my words clear? Okay, great. So thanks for the introduction. And the title of this talk is the Iterative Process Learning for Large Language Model Post-Training. And so we'll focus on the post-training, post-training and especially the process learning stage, the very last stage of large model training pipeline to make a Chat-GPT. And you may also know this stage as the RLHF or alignment. And so we will start with our motivation, where we can study the process learning as a sequential decision making. And to establish the context, we will introduce the concept of RLHF. And also, in the set section, we'll present our main results, which is online iterative RLHF framework. And finally, we will discuss how to implement our framework with the practical and open source codebook RLHFlow. And so, since for the last speaker, so a lot of introduction of all these concepts make my life much easier. So it's helpful to contrast the supervised learning to the decision making to illustrate the idea. So in supervised learning, we have a batch of data, and we input the data to an algorithm to learn the input-output relationship and to predict the patterns from the passively observed data. And examples of this type of problem include images classification and speech recognition. However, in decision making, we are kind of like learning in a feedback loop with an external environment. So we actively gather information by sequential interaction with the environment. And so the main difference here is that our decision will influence the data we collect, and so the information we receive from the external environment. And the problem of this type include the recommendation system, robotics, and game playing. To be more specific, for a decision-making problem for capital T type steps, at each type step, the decision maker on the left-hand side will receive some context from the environment and make some decision pi t. And the context and the decision will jointly determine the reward signal RT. And the decision maker will also observe some observation OT from the environment. So to connect with the language model, the context here is just the prompt, and the decision is like a distribution of a response, and the reward is related to the human preference, which will be defined later. And the observation is like some potential external message. So for many cases, it's empty, but we will also talk about some example that the external message can be not empty. And the fundamental challenge in the decision making is a so-called exploration and exploitation trade-off. So for one thing, we want to focus on a good decision based on a history and avoid a bad decision to maximize the reward. But in the meantime, we need to try some new decisions to learn the environment. So this is because, as we mentioned before, the decision of the decision maker will influence the data we collect, so the information we receive. And so the decision-making problem is something that's relatively well established in the past few decades compared to the more new learning paradigm of process learning. So the main research problem here is that can we design some principled process learning algorithms under this online sequential decision-making framework? And so to establish the context, we'll have a quick introduction to the classical RLHF framework. And so we want to integrate the human preference into a language model. So a naive way is that we include a human rater in the loop. So we input a prompt to a language model and ask the language model to generate some responses. And here we have two responses, A1 and A2. And then we ask the human to determine which response is better. And we bring all these prompt responses and also the human signal back to the language model to update the parameter or to improve the generation quality. But unfortunately, this framework, this naive human in the loop framework is not scalable because you cannot imagine that between two updates of SGD, you have to wait for a human to give the feedback. So what we do is that we impose some additional assumption. And the assumption, so one widely used assumption is the so-called Brateri model. And in Brateri model, we assume that there exists a ground truth reward function. And this reward function can assign a scalar reward to any prompt and response pair. And the probability of the response A1 is being preferred over A2 is exactly the softmax of the reward value. So this reward function is scalable because basically we can query the reward as many times as we want. And under this Brateri framework, So under this Brateri framework, the learning objective of RLHF is to maximize such a regularized reward. So this target is like a trade-off between two targets. So for one thing, we want to optimize the reward, but for another thing, we don't want to push the optimization to move too far away from the original policy, supervised fine-tuning policy Pi0. And so now we have our classical Chat-GPT framework. So it's like a three-stage framework. So first, we collect some data. So this can be either passively observed data or data from our original behavior policy. And for most of the case, it's the Pi0, the supervised fine-tuning policy. And then we just construct a proxy reward as the maximum likelihood estimation of the Brateri model. And finally, we can run some IR, either PPO or something, with respect to the proxy reward plus some regularization. And we get our final aligned model. Yeah.
Because there is no unique solution for the reward function, right? Because especially with the comparison, you can always scale the reward, and you will maintain the same ranking. So especially when you're doing this kind of regularized setting, like how do people usually maybe put some kind of regularization even while doing the MLE?
Yeah.
Then a reward that plays well with the scaling of the log pi over pi naught.
So in practice, we don't do the MLE. We always add stopping, and I think this is a very strong regularization. Yeah, but for simplicity, we just take the MLE in the discussion and to discuss the theoretical inside of this framework. Yeah.
Sorry, I missed your last sentence. You mean in practice, people do not do MLE, but instead doing what?
Oh no, we do MLE, but we do not train to the minima. So we always do some early stopping,
And the MLE somehow explicit for the Brateri model. That's what the first.
Yeah, Brateri model. Yes.
The sample.
Yeah, sample. It's a MLE on the sample. The data set that we collect from the very first step. Yeah.
Even if you get the exact probabilities, not just samples, even then the R is not unique. No, not for Brateri model. The scale. So because if we are, I was trying to understand how that is taken care when you're doing also RL with the scale divergence.
Yes, so
I think so. Technically, the solution of MLE is not unique, but I think we don't really need to worry about it. So first, we always do some stopping in practice, and for theory, you just take the ending of that. It's okay. Yeah.
Also, your eta is tunable, right? So even if R has some scale, you can always just put make the eta appropriate. Yeah. Okay.
Good. In theory, yes. I was curious about how they do that in practice.
So this framework is very successful, but it also faces some challenge. So it's about generalization and distribution shift. So, this problem is so-called the proxy reward over optimization. So which means that a high proxy reward we construct doesn't necessarily lead to a better performance on the downstream task. And so this is because the output of the language model easily falls into the out of distribution region of our proxy reward. So again, I will introduce this figure again. So at the very beginning of our training, both of proxy reward and our ground truth reward aligns very well. So even we optimize against this proxy reward, the underlying ground truth reward also increase. But as the distribution shift becomes larger and larger, our proxy reward is no longer reliable. And optimizing with a proxy reward will eventually lead to a decrease of the ground truth reward. And so our solution is very simple. It's to just, we should think about parse learning as the online decision making. And so what we have done in the Chat-GPT framework is pretty like what we have introduced in the supervised learning. So what we do is that we add a loop, as we observe in sequential decision making, to iteratively deploy our intermediate aligned model to generate new responses, and we ask the rater, the human labeler, to give a new label. And we put all this new data back to the historical data, and a new iteration will begin. And so I think one straightforward intuition to convince that such a sequential framework is helpful is that the new responses and the ground truth labels from the human labeler can mitigate the auto-distribution issue of the proxy reward. And so we are ready to present our main agreement framework. So what we do first is that we divide the learning into a capital T batch. And for each type iteration T, we first have our main agent, and the main agent will exploit the historical information that's stored in the historical data. And so specifically, we have our PyT1, which is exactly something we have done in the Chat-GPT framework. So we compute the MLE reward, and we compute the optimal policy with respect to this MLE reward. So it's kind of like we want to use the historical information that we have collected so far. But to ensure that you can iteratively improve your PyT1, your agent's policy, you have to make sure that the newly collected data will bring you enough information. So that's why we have a second policy, which we call this agent enhancer. So instead of learning the optimal policy, the goal of the enhancer is to help the learning of the main agent. So this enhancer tries to explore the underlying space by maximizing the uncertainty relative to the PyT1. So we will give a concrete example of an uncertainty estimator. So here the intuition is that, so given history, if we are uncertain about this direction, it's probably if we explore towards this direction, we will get more information. So that's why we want to have an asymmetric agreement framework. So one is to use the historical information, and one is to explore. And after designing these two policies, what we do is just collect M new samples and to ask the label from the ground truth laboratory model. And so to illustrate the idea, so we present a concrete example of uncertainty estimator. And so if we assume that, so in a simplest case, we have a linear reward. So the reward is linear in some feature map, which can map the prompt and response pair into a d-dimensional vector. And then for any two policies, we can define the uncertainty estimator or the information gain as like, which is just like a feature difference, the projection of the feature difference back to the historical feature course matrix. And so the reason why we always have a feature difference, or we always evaluate the uncertainty in terms of two policies, is because in RLHF, we always learn from the relative feedback. So that's why we always have two policies. So that's why we always care about difference. And so you can imagine that if so we have a direction, and we project this direction back to the historical feature coverage matrix. And if this quantity is still large, it means that this direction is not well covered by our historical information. So that's why we are more uncertain about this direction. So we want to explore toward this direction. And yeah, so this is a linear case. You can definitely generalize a little bit to a non-linear setting, but we don't want to dive into the details of because a lot of mathematics to this process. And so here's the main theoretical guarantee if you want to run this online iterative RLHF and with the exploration. So if we run this online iterative RLHF framework with the batch size, which is d over epsilon square, And you run this framework for at least d times up to some log factor. And then with high probability, you can really find a good policy that is converged in both of regularized reward and also the divergence between the policy and the optimal policy. And so the advantage is that we already have an algorithm that is probably efficient, but we also have some disadvantages. So first, the iterative human feedback is very expensive, especially for the open source project. And also, it's not clear how to construct the uncertainty estimator for general neural network. And so we will discuss how to mitigate this issue in the next section about how to implement this framework. Yeah.
The expensiveness is that the number of rounds is large. Like basically, you were thinking of like the cost as being like every time, like every kind of round of the algorithm, you need to go pull.
Yeah, it's about a round. So like if even you have the same number of a total query of a human, if you always assign this query just once to the labeler, compared to the iterative training, iteration is also much more expensive. Yeah.
So just trying to connect this to other things that we know about. Should we think about this as doing like active learning of the proxy reward function?
Yeah, it's kind of like this, but we don't. So I think in the study of active learning, you always try to select the some prompt, right? You always try to identify the prompt that is important about your learning. So so if you have a strict meaning of the active learning, so this is not so related to active learning, but I agree that this kind of you want to actively to gather information to explore the space.
No, I mean, I guess you're saying that for active learning, you want to be able to do well on a test distribution, and you know that test distribution. And in this case, you don't know the test distribution yet, because you don't know where the policy is eventually going to end up. But you could try to do well at around the current trajectory, and then you're moving data set aggregation because you're not throwing away the old data.
Yeah, and then you will actively gather some new information from some ground truth data. Yeah, I think this is what we do here.
Yeah, there might also be a connection to imitation learning. So I mentioned data set aggregation, so I was thinking of the Dagger.
Oh, Dagger, yeah. I think it's all involves some online iterative learning, online iterative exploration in the framework, so that's a lot of similarities. Yeah, but I agree that the core similarity and also the essential idea here is that you really need to think about the problem as a sequential decision making. So a lot of technical from a decision making framework can be used here and to lead to this guarantee. Yeah. Yeah.
And so I guess somehow like the way that multiple rounds help you here is that you mitigate the distribution shift from round 1 to round 2.
Yeah.
Is there a sense in which there's like a kind of matching lower bound here that if you don't do at least some number of rounds, then kind of in some worst case sense you have to suffer a worse loss?
Yes. In a theoretical IR, there's a coefficient called the decision estimation coefficient. So which means that so here we consider the linear model. So here the dimension is kind of a capacity of this problem. And so there's some matching lower bound says that you have to explore such a so many rounds before you can really learn the optimal policy. Yeah.
I think for this particular case, you can probably just construct counterexample by just multiplying bandits, right? Because then equal to D, and like I guess usually it's the standard one action and reward, but for preference, I will bet like it's still gonna be like.
Yeah, but I think for a DEC, there's a general lower bound for, yeah.
Okay.
And then we are ready to discuss how to really implement this framework in practice, taking the cost and the time, especially for the open source community, into consideration. And so this is the overall pipeline we want to do in our online iterative RLHF. So, the very first thing we want to handle is how to construct a ranking model, because for the open source project, we cannot afford to create a lot of like a CS PhD to help us to label the data as OpenAI does in the Strawberry model. And so what we do is that we try to explore the different methods to construct the ranking model and based only open source data. And also we want to include some heuristical way, like we increase the length penalty, final result checking for the math problem or coding when the ground truth answer is available. So the very first approach we want to try is to construct a pairwise prompts model. And so a pairwise prompts model would take like a prompt and 2 responses as the input, and it directly predict the probability of the first response is being preferred given the prompt. So in other words, we drop the assumption of Brattain model. So this is a function class with larger capacity compared to the Brattain model. And so for implementation, what we do is that we formulate this problem as an instruction following task. So you can see here we have an instruction, a prompt to a language model with a prompt and with a context prompt and also 2 responses. And we use the probability of the language model to predict certain token as the estimation of the probability. And here we use the probability of the language model to predict token A as the probability estimation of the first response is better. And another thing we explore is that we want to explore some more fine-grained signal. So this is because to evaluate the quality of your response, there are a lot of attributes. So you can make a more fine-grained characterization. So here we have a helpfulness, correctness, coherence, and complexity, and verbosity, a lot of things. So what you do is that you first construct a multi-head reward model from these different criteria. And after this, we want to gather and combine all these different attributes into a scalar score. So you can really use especially for the deeper IL method. So we develop a mixture of expert aggregation. So we train a gating layer. And this gating layer would take the embedding of the prompt as the input and decide the coefficient to combine the multi-objective and multi-dimensional score vector. So this is because we believe that how to combine these attributes depending on the context. So if you are encountering a prompt that will possibly trigger some unsafe responses, in this case, the safety score should be put larger weight. Otherwise, I think the helpfulness is more important. And so it turns out at least 2 types of function class, even with only open source data, we can train a very good reward model. So this is a result from the reward benchmark. So you can see our multi-dimensional reward ARMO, and also our pairwise prompts model rank pretty high in this reward benchmark, especially the ARMO ranked 2nd in the benchmark that is surpassed a lot of model that is even much larger than our base model. So our model is based on Llama 3A billion. And also this open source model have been used as a ranking model for many follow-up research project. So this is, yeah.
How is the score assigned here?
You mean this the overall score?
It's like the second column.
It's just the average of different type of task.
I see, but the training of the model doesn't get to see these categories. Like
Yeah. Just for the training, yeah, we don't have the category of the task. Yeah.
And humans label these like
yeah, let's the human divide a lot of test set. I think there are more than 20 test set, and they divide them into different categories. So we have chat, safety, and reasoning. So this is the very first step. So we construct some ranking model based on the open source data. And the second step is that we want to approximate the exploration policy. And unfortunately, in general, the uncertainty estimator is still an open problem for the neural network. I think it's still a very promising way to direction to do. But here, we just adopt some heuristic strategy to maximize the sample diversity. So this is because if you look into the uncertainty estimator, so what you can do is that you can maximize or at least enlarge the feature difference between these 2 policies. And so that's why you may, so intuitively you can try to maximize the sample diversity so as to enlarge the information you receive from this exploration. So the very first thing we do, which is also a very popular choice in practice, is that so-called words of n sampling. So it means that you sample n responses, and we just use some reward model or some ranking model, either the ARMO or pair express model, to rank all these responses. And you take the best model and the best response and also the worst response to construct a pair. So kind of like enlarge the difference between these two responses to enlarge to improve the sample diversity. And the second thing is that something used in the Llama project is that you're tuning the sampling parameter, especially the temperature. And the very last thing is that you can collect the data by different checkpoints. So when you train your model, you possibly will update the model like 1,000 steps. So you can save a lot of checkpoints along the way. So you can use all these different checkpoints to collect the data and to maximize the sample diversity. And the last thing we want to discuss is that how to really train a model. And so the classical way is to do a PPO or DeepIO method. But unfortunately, even in a private neural network, which is much smaller than a large model, it's still very tricky to get the PPO work. And so especially for the open source community, to be honest, so far, I don't really see some good open source models are trained by PPO. So there have been some alternative approach designed to be to replace with PPO algorithm. And one of the most famous algorithms is the so-called direct perms optimization, or DPO. And so this is a very elegant algorithm which can be described in just a few equations. So let's go through the mathematical details here. So the key observation is that the original regularized optimization problem, it admits a closed form solution, so which is the so-called Gibbs distribution. So which is like a product between the original reference or supervised fine-tuning policy and also the exponential 1 over its times the reward value. And so we have a closed form solution. So maybe we can directly use this closed form solution to sample. Unfortunately, no, because you also have the partition, just normalization constant of this distribution. And to really compute this normalization constant, what you need is to go over all the responses, all the potential responses. It's at least exponentially large, or basically infinitely many. But we can still try to leverage this closed form solution. So what we do here is that you just take a log on both sides, and you can reparameterize the reward by the policy. And so now you have such an equation that connect the reward and the policy. So what you do is that instead of first constructing the MLE of a reward, you can directly plug this expression of a reward by the policy into the equation. So you can directly optimize the policy instead of first constructing a reward function. And the fact is that, so if there's no optimization error, the optimal solution of this DPO algorithm is the same as the RLHF framework. But the advantage is that it's more like a supervised learning target compared to the PPO algorithm. So it's much more stable. Yeah.
So the premise is the language model implies some implicit reward model. The question is it a good reward model?
No. We have a very recent paper, I think released last week. We just tested the accuracy, in-domain accuracy of scalar, just the BT reward and the language model as a reward by the DPO. And the takeaway is that the DPO is much worse in terms of generalization.
Thank you.
Yeah.
Right. Yeah. Related question. It seems to me it's always like a chicken and egg problem, right? So during training, every time you get an online policy, and then whenever you use DPO, you are treating that this online policy is optimal, and then you derive a reward function from that. But if that current online policy is very bad, and then you use the current to derive the reward function, and then you actually want to maximize that reward function, will that lead to like a further worsen of your current policy in practice?
You are still using unit data.
Oh, okay.
Okay. Yeah, I think the fact is that so you have a bunch of offline data. So in this offline data, you have some prompt responses and human signal. So I think the fact is that you can do two things. So first, you train MLE reward based on this data, And the second thing is that you can directly optimize the policy using the data set. And I think the answer is that these two policies are equivalent, at least in the ideal case.
Yeah, I think that was his question. Somehow, like these two things are only equal at the optimum, but they're not equal away from the optimum. And then it's like a leap of faith, sort of like that. This is going to also work even where you're away from the optimum.
Right.
I think it really depends. So personally, I think the deep IL method still like performs better in practice, and especially there's still a lot of problems of DPO in we haven't addressed in practice. And so the question is that whether we don't really optimize to the optimal point. So whether this policy is still, I think it can still improve your original policy a lot. So your final DPO policy is better than the super fine-tuning policy. But whether it's better or it's worse than the RLHF policy, to be honest, I don't really have an answer to.
The original Pi0 is already pre-trained on batch data, so it's not too bad. And then initialize the Pi-R at each iteration, which is very close to Pi0, so that's also not too bad. I guess in the worst case, if I just I don't have the pre-training stage, I start with a random policy and then apply this DPO. Shouldn't be hard to construct like a worst case where the reward function is really, really bad, right?
Yeah, but let's know what we do in practice. So in practice, what we observe is that the final DPO policy is still much better than a SFT policy. But whether it's better than RLHF policy, I think the problem is that we don't really train a good RLHF policy from the open source data, open source community. So that's why we really need a list algorithm. Yeah.
So is it fair to say, like, that you think the RLHF policy would be better if you could solve the optimization problem, but somehow maybe because it's like a less stable sort of like RL problem that you need to solve, like it's just more difficult to actually solve?
Yeah. So this is because for the RLHF, or we just say PPO or IL, you don't really depend on the BT assumption. So for the PPO, you only need a reward function. So you can use a much larger and much complicated reward function to do PPO training. But for DPO, you always are constrained by this BT assumption.
Yeah, and also to add to that, like there was also this very interesting ICML paper this year, which did a lot like they like it is literally titled "Is DPO better than PPO?" Right? And they did a lot of like empirical studies, and they do, at least in their observation again, like I think as you were pointing out, they do point out that it's not really like it's because of for practical reasons people might be using this, but PPO seems to beat DPO in many. So it's not a settled debate.
Yeah, I think one. I think one straightforward explanation is that so when we say these two is equivalent, we assume that the transformer can approximate both this scalar reward and this implicit reward perfectly. But clearly, I think the implicit reward is much harder to approximate by our current limited transformer. So we are ready to finally present our main experimental result. So what we do is that we do the online iterative RLHF, and with our model. So the base model here is a fine-tuned version, which is also based on the open source super fine-tuning data set. And we iterate the online iterative RLHF with the direct perms optimization for 3 steps. So what we see is that for the 4 benchmark, which is the benchmarks that regularly used to evaluate the instruction following ability and also the helpfulness of the model. So what we can see is that through the iterative training, both of the 4 metrics of this benchmark increase iteratively. And especially, we outperform the offline version, which is only take one iteration of training significantly. So I think this should illustrate the benefit of iterative training by continuous explore and interaction with the underlying rater or underlying response space. Yeah.
What happens when you want to train such a model with multi-turn preference? process. Like you have prompt, response, second prompt, second response. So you have a dialogue, and then you prefer dialogue over response. If you have such a data set, how would you go and implement the EPO like algorithm?
You mean you have multi-channel dialogue or?
Like multi-turn interactions.
So I think one thing you can do is like you can extract the multiple prompt from a multi-turn dialogue, right? And I think this is one thing we can do. And I will also introduce a multi-turn version of DPO I derived very recently in the next few slides.
Am I right that the typical thing is each response gets its own reward and is treated as a separate problem? So there's a first question from the user, and then you can rank different responses. Given that you have question, answer, second question, you rank different responses to the second question.
Yeah, let's you extract multiple prompts from a multi-turn dialogue. Yeah, this is a very useful and also widely used approach in practice.
Yeah, so it's a lot like autoregressive training, where you're doing teacher forcing in effect. But the prefix is fixed by the model so far. Oh yeah, I guess teacher forcing is not fixed by the model so far. So sorry, but you've got reward for it. You've got feedback on the return separately. But you just said you have a new method, which might be different from that.
I think that's. I think the same from what you say. Yeah. And we also evaluate our model on some academic benchmark to evaluate the model's ability in math and coding. So basically what we can see is that our model achieves comparable results compared to the model trained by Meta. And our model only uses open source data and it's trained by our online iterative algorithm framework. So I think the conclusion here is that we really have some robust recipe to do the post-training of a larger model. And yeah, okay. So why I want to generalize the result a little bit is how to relate it to the first question is how to extend this framework into the multi-turn, something we are really. Because so far, we always treat the problem like a bandit. So we always treat all the response as a meta action. So here, I would like to introduce the multi-weighting example, which is so-called multi-turn to integrate reasoning. So first, the user will enter some prompt, which is a question about some mathematical problem. So this is serves the initial stage of this multi-turn. You can think it's just a MDP. And so first, the assistant, our model, will generate some intrinsic reasoning, just like regular things what we do when we prompt the language model. But in addition to the intrinsic reasoning, the model can also write down some code to call the so-called tool, external tool. And once we detect the model write down some code, what we do is that we'll run some external Python interpreter to return the running result of this code. And so here, the key difference is that we have the external message along the way of trajectory generation. And we also define, similarly, we also define the notion of state, which is the history at the beginning of a step edge. So you can see that the prompt and also the intrinsic reasoning, and also the external observation from the external Python interpreter. And so what we do is that we still want to derive direct personal learning algorithms because it's much cheaper compared to a deep IO method. And so we still assume we denote the trajectory as a tau, and also we denote the completion, which is we delete the initial prompt from the trajectory as y. So we assume that we still have a BT model, and it can assign the prompt signal over the trajectory, and especially on the completion of the trajectory. And here, our learning objective is that still we want to maximize the reward function, and also under a KL constraint with some KL penalty. But now we send over all the test steps. And also here, we for simplicity, we assume that we have a fixed number of rounds. And so after some mathematical derivation, what we can draw a conclusion is that we can also have a reparameterization trick between the policy and the reward model. And between a model and the policy, because now we are considering MDP. So in addition to the reward function, we also have a transition matrix. And so what we see is that in addition to a turn A, which is something similar to what we have in a single turn DPO, we also have a turn C, so which is the difference between a random v-value and the v-value, but we take expectation in terms of external message here. And unfortunately, for general case, the turn C is not 0 because we always have some randomness of when we call in the external to and observe observation. But we do have 2 cases where we don't really need to worry about the turn C. So the first thing is that when we only have 1 step, so it's original DPO. And the second thing is that we have a deterministic observation. And so definitely, if we don't have an observation, then it's deterministic. But we can have a little bit more general, where, like for instance, when we really write down the code and see the execution result of the code, I think this is also quite deterministic in this example. And so the takeaway message is that when you do this, is you just need to run a regular DPO but mask out the external message. And so we do the experiment also in an online iterative framework with the mathematical reasoning task. And so as we can see, so we use the prompt set from the benchmark, the training set of the benchmark math and GSM-AK. And the reward here is just the binary reward to check whether this trajectory is correct or not in terms of the final answer. And what we see is that we can achieve significant gain in terms of final test accuracy. And also, if we look at the result of with the JAMA, we can see with the online iterative training, the final model is much better when you only run the experiment for 1 iteration. Yeah.
Do you have a sense qualitatively what improves when you do the multi-round version, multi-turn version compared to the single one?
You mean a single turn DPO and multi-turn DPO? Yeah. Yeah, we have some result here.
Oh, no, numerically I see, but like qualitatively, do you have a sense of like what gets fixed if you do multiple iterations versus multi-turn versus 1?
Yeah. You mean why some iteration, why this multi-turn version improved? Yeah.
What kinds of errors does it fix, I guess?
I think I do have a backup slide. Yeah. Sorry. Yeah, we can look into this example. So what we do is that we mask out the external message, right? And so if we look into this example, so our model write down some really bad code, and the external message is just a mass of very lengthy error message. So if you want to because you know the DPO is like a contrastive learning, so sometimes you will force the model to increase some probability of a positive response, but reduce the probability of negative responses. And so sometimes you are forced your model to learn this predict this external message, which is very low quality responses. So if you do not mask the loss in terms of this external message, you will definitely hurt the overall performance of your model. Yeah. Another, I think, intuition is that because when you really want to optimize your policy, the external, the distribution of the external message is something you cannot change. You cannot optimize with respect to the external distribution of external message. So if you still want to predict optimize the loss in terms of this external message, you would also do some wrong objective, so eventually hurt the performance. And so we open source all this model code and also data set and also hyperparameter to GitHub and Hugging Face. And yeah, we have observed a lot of follow-up work use our code, especially our model, our reward model. And
Another question.
okay.
So, for the multi-turn, do you observe that credit assignment becomes even more challenging? Like, for example, if the model is really bad on one of the turns of the dialogues, then it gets penalized for all the outputs in all the turns.
Yeah, I think this is something that you really need to do if you want to improve the model's performance. Like you are talking about a process reward, right? I think process reward is the key to really improve quality of your model. And I think the problem here is that we only assume the trajectory level preference. So the capacity of this model is still limited. So it may fail to capture the process reward signal you mentioned. But unfortunately, it turns out what you can do is that you don't really can do much about the process reward if with the DPO framework. And I think this is also a message that, especially for reasoning task, the BT model induced the DPO is not so appropriate, and we must return back to the PPO training. But for open source project, you always need to balance the cost and the performance. But what we see is that the DPO is still like a competitive baseline and lead to considerable improvement. So that's why we use this algorithm in our project.
Thank you.
It's not a question. It's like, what makes Bradley Terry special here? Like, why not take some other distribution? I mean, like, you can cook up a bunch of distributions over, like, a 0-1 outcome for what, like, who's the winner, who's like the loser.
Yeah, exactly. Actually, DPO is the most popular algorithm here, but actually Google has an algorithm called Sleek, and which is slightly 2 weeks earlier than DPO. So you can show that these two algorithms are equivalent, except for the logistic loss and the hinge loss. So exactly, you can try different link function to so it's basically a different assumption on a preference signal. And actually, someone has a proposal called generalized DPO that includes logistic loss, square loss, and hinge loss, a lot of loss. But they don't really have a different performance. So yeah, it doesn't help. So that's why DPO is still the most widely used algorithm.
So the coding example you gave, like the interpreter message happens at the very end, right? Like, are there examples in actual training where after receiving the message, like the policy takes further actions?
So in this example, like, so the code so we have multi-turn, and the turn is marked as the model decide to call an external true.
Right.
So this process will iterate for multiple rounds.
Right.
So I think for your question, you can you just define the action as a more broader concept. Like,
I'm saying this, but I'm saying like the example you give in the backup slides.
Yeah.
It seems like the very last thing you did is to call the interpreter, and there's no further action after that. I'm saying
this process can be iterated for multiple rounds.
I mean, like, and this actually happens in the actual data.
Yeah. So once the model can observe the output from the external code interpreter, what you do is that you put all this together as a history, and you input this as a prompt again to begin the next step. So that's why it's called multi-turn. Yeah. Okay. I think we have two takeaways. So the first thing is that the RLHF really benefits from the continuous online exploration through interactions with the rater. And so this where sequential decision-making tells us, and it really works pretty well in practice. And the second thing is that the online iterative direct person learning is a robust recipe to make good chatbots. And so what we see is that like past 1 year or 2 years, so what we see is that a shift from the Chat-GPT framework to the Llama 3.1 framework, and we have introduced this online iterative framework, and we also missed something like a model merge and also the so-called best of fine-tuning. I think the next speaker will talk about this also very competitive and elegant algorithm. And I also want to comment a little bit about one thing is that, well, can we really think the human rater generalize well? To some degree, yes, but it's also no. So we can see that, so what we observe is that both the human rater and the strong GPT-4 will bias towards certain format. So what we do here is that we collect a lot of open source preference data set, and we compute the ratio of the samples that containing certain pattern. And this pattern can be like a longer responses than response containing the emoji, and also like a bold or list, a link. And so if we observe that the ratios in the preferred responses and the ratio in the unpreferred responses are different, this can imply there can be some bias of the rater toward this certain pattern. And what we observe is that for both the human and GPT-4, you can see some clear difference of the ratio in preferred responses and unpreferred responses in terms of a different pattern. And so I ran experiments yesterday. So what we do here is that we do a reward modeling first. But here I attack the reward modeling by adding 1% of the samples whose preferred responses are with the bold pattern. So this reward model will be biased toward the pattern bold. And what you see is that along the way of iterative training, the ratio of responses containing the bold pattern increased significantly, especially compared to the baseline first the super fine tuning model and the offline DPO. So this means that when there are some shortcuts in your ranking model, online iterative training will significantly amplify this bias. And unfortunately, what we see is that even like a GPT-4 or human, we still have such a shortcut. You can also see from this other very famous open source data, you will also observe a significant bias in both the bold pattern and also the list pattern. So I think this can teach us 2 lessons. So first, you need to explicitly consider this thing in your algorithm design. And the second, for evaluation, for the benchmark, you also need to take all this consideration into consideration. And also, when you ask the human to give the rating, to give a signal for your learning, you also want to write down some rubric to mitigate such a bias. Yeah, I think that's all I have for today. And to see whether you still have some question.
Okay, we'll be back at 3:30. Thanks one more time.